Today, what I'm going to present is what we've done at Oxa MetaDriver. So it's a collective work. It's not just my personal work. It's the work of the team I am working with. A bunch of very good people, very talented, and lots of fun to work with them. And so the talk's about accelerating machine vision for autonomy. So as you may or may not know, Oxa is a company that works scale up, I would say now, in the autonomous industry. We're mainly targeting industrial autonomy needs as of now. We are based in Oxford in the UK, but also expanded into Toronto and Florida, if I'm correct. I don't know exactly where, but somewhere in Florida. And but for the part of us, we are mostly based in the UK, people of that team. So now what do we want to talk about, right? So the overview of the presentation is a little bit of introduction about what is machine vision and how do we use that for autonomy. Then we're going to present the different parts of this kind of end-to-end automated pipeline that we've made. So it goes from route planning to data extraction to sampling of vision data to then large-scale labeling and so on. How do we train models and where do we go from there as well? Because that's probably an interesting insight. So for the introduction, yes, basically what we've made is a bunch of tools that are used within 51 and also in conjunction with 51. And it's an automated workflow that really covers from start to finish. So from data collection, so literally getting a car to collect data, or cars, plural, and then to deploy models in vehicles. So we've made a workflow that is, we claim to be explainable and scalable architectures and design, and we're able to generate curated data sets from very large amounts of data. It also offers things that are quite interesting, like search capabilities, so a search engine and a multi-modal search engine. I'll come back to this later with nice videos. And that's quite good for general usage and also anomaly detection, which is something that's important for compliance purposes. We have stuff like out of distribution data augmentation, which is a product that's been released on the Google Marketplace. I'll come back later to a little bit of advertisement for that. And yeah, that we're able to build robust families of model with a few clicks, thanks to that. So the first part is collecting data. Capturing data is quite key. Before I started Oxa, so a bit more than a year ago, somebody said that phrase, just drive somewhere interesting, mate, I don't know. And obviously telling that to someone's job is to drive is a bit tricky because what is interesting for you may not be interesting for them and vice versa. In the concept of machine learning, diversity and quantity are really core concepts to improve generalization. And diversity in machine learning, depending on the task you're dealing with, depending on the research area, whether it's vision, language, et cetera, has really many facets, right? And even in the terms of just vision, we have visual diversity, semantic diversity, topological diversity, so the layout of the street, et cetera. So it's really a sort of really big sort of bunch of concepts, but it's difficult to find the root cause of each and every of them, the nitty-gritty stuff. So, but one thing that does help is that if you maximize geospatial independence, it really, really helps. Because if you go to two different streets, then you're not going to see the same things, and they may repeat themselves a little bit, but the further you go and the more diverse you keep being, the more diversity you're bringing on all of these topics. So one thing that we did is something called pathways. Which is basically they're all packages in Python. They're obviously internal packages. We're not, it's not open source, sorry. But basically based on an arbitrary area, a map that you can grab from OpenStreetMap and start an end node. So these, you see the green dots and the red dots on the image. We can sample randomly intermediate nodes and then solving things like Dijkstra or A stars. So which is shortest path between nodes. But instead of just taking a cost function that is, say, the shortest route or the shortest route in distance or time, we're going to add cost function which have this dry, so do not repeat yourself. Components which are going to make it that at every further iteration is going to have to stray away from repeating itself, otherwise the penalty will increase. And once those routes have been computed, we send those routes now to be to the AV's GPS, and people will start driving on those. So this little thing has massively improved the coverage and the diversity. We've covered significantly more distance than in the last 6 months than ever before. And here I show a little map about Oxford, but we're going quite around England, basically, and a bit further. So this is basically growing, and we ensure that we don't repeat ourselves in order to grow the data we can learn from and build data sets upon. So the first thing after that is extracting the data that we get from the car. So AVs need to run in real time. Real time means C++, lots of components that are very well engineered, and so they need to use special data structure to communicate between the different components of the car. Now, I don't have the pretension to say I know exactly what's going on in there. It's a very complicated thing and it's a whole different field. But what we know is that data scientists, so people that are more like me and my colleagues, should really not use these data for data science, those structures. It's dangerous. It's going to be very error prone and really not in the overall way to deal with things from a machine learning perspective. So Jamie, a colleague and friend of mine, made those two things called Rosetta and Alexandria, and Rosetta translates those structure into open file format. So we convert from protobuf to JPEG images, point cloud, and you name it. And now Alexandria, based within 51, organized it all into 51 data sets where we group the data, as you can see on the screenshots on the right, with respect to timestamps, the GPS, the SIG-stuff data, and etc. So all of this, for example, cars, they have a bunch of cameras, sensors on them, and all the sensors are asynchronous. So you have to sort of group things a bit intelligently to know to associate these images together in that LiDAR frame, but not this one, because they're closer in time, for example. So yes, one thing that is important now is we have lots of data. And we need to be methodical at dealing with it, because otherwise you're just going to end up doing suboptimal things. And AVs do generate a lot of data. And when I say a lot of data, is 500,000 images per hour on the sort of previous generation of AVs that we have at Oxa. And so that's a big number, because if you drive 8 hours a day, etc., every day of the week, every week of the year, that becomes now in the billions of images. And there's a lot of redundancy that is caused by temporal causality, because the car is moving forward. So basically the front and rear camera see little changes that are basically correlated, like the driving phenomenon is the speed of the car. And the side camera do see a little bit more action, but still. And this is where we need to talk about the fact that periodic or random sampling, so sampling every other second, or taking a frame 10% of the frames randomly throughout the whole log of the day, is not sufficient nor efficient, because you might sort of miss the little gems. So we've come up with a multi-tiered strategy where we use something that you guys probably all know, is to use other neural networks, pre-trained neural networks like ResNet 50, DynoV2, and many more, to generate different embeddings. And then we're going to compute some uniqueness by approximating distance matrices of elements with other elements of the set. And when I say approximating, is because this problem is quite quickly intractable, because if you have n sample, you're going to have a distance matrix of n squared, and by n, so that's going to be a problem. So what you want to do is to approximate those well, I don't know if I should talk this out. Basically, you're going to approximate kind of as you would approximate integrals. That's how we should phrase it. And the decision basically is now based on the expected value of what it would add to add this or these elements with respect to the existing set, so that you have a way to iteratively build a data set and shake things down together. So that was for squeeze and sift. One thing that is to take away is that, yes, we are trying to extract the most valuable samples from very, very large amount of data. For example, from 100 hours of driving to 1 million images. At first, here on the left, you see a log that has, so it's one camera, and you see those little paths. So when projecting, so this is done with 51 as well, pretty neat. Projecting high dimensional embeddings, which are basically continuous or nearly continuous in high dimension, when you project down in 2D, you see those paths appearing. And basically those paths, how close these points are next to each other is how redundant is your data, basically. And so what you want to do is to break these dependencies because they bring nothing to the network except extra compute and very little reward on top of that. So now the next part is that once we have selected this nice data, as you could see it on the right, those nice uniformly distributed points, we want to label them. And we do want cheap machine annotation and not expensive human annotation. But cheap does not mean bad because, as we all know, and pardon my French here, if you put shit in, you get shit out in machine learning, and we don't want that. So we want to have good annotation. We want to employ what's best out there with respect to state-of-the-art, for example, models, and we want to use and get the most out of them, ensuring that the quality is always there. And what's good with that, with these automated machine labels, is that that can accelerate greatly as well exploratory research. The same way that you can sort of cluster embeddings in high dimensional space, you can do so with the labels that you have against your image. So again, that's another way to explore the data from a more semantic and accurate context. Now, we need a lot of data to train, we need a lot of data with quality annotation to train better models. And this is what was coming to my previous sentence. And so we've built another tool on top of 51 that basically out of the box for any serializable model, which is done with Onyx, w.r.t, TorchScript, et cetera, can run inferences to annotate those data set coming from the car, basically. We also re-implemented more manually some trendy, spicy models that help because sometimes you can't serialize everything. Sometimes research code is subpar. I'm sure you guys all know all the struggles with this. Now, going back to this, so a little bit of result. For example, here, one example of the many pipeline we can run is if you take a model such as grounding Dido, which basically runs object detection with respect to language prompts. So you can guide it with language. Instead of having a fixed taxonomy, you can pass in your own list of prompts that you want to find within the image, and it'll try its best to find it. Then on top of this, we run segment anything, which is instant segmentation that take those detection as prompts, so what you see on the left, and outputs you what you see on the right, which is now the instantness related to those. And finally, we post-process all of this in order to retain the most convincing detections and segmentation instances, basically. This whole pipeline is fairly cheap. We are here using a cloud provider, Google, GCP, and basically an image costs now 10 to the minus 5 to the minus 5, basically, sorry, dollars per image. So yeah, so that's another cool thing, I guess. Now, moving on, we have, so this is Edward, a colleague of mine that made a really awesome tool, which is a cross-modal search engine. So perhaps you guys have heard about Google reverse image search, which basically you can give it an image and I'll try to find associated images to it. Well, think about this like that, but cross-modal. So first, I'm going to preface this. This is useful because there are some adversarial situations with respect to the behavior of the car, with respect to the behavior of the other cars and other pedestrians and other actors on the road. And it's crucial for autonomy to be prepared against those. When sometimes we need to search and find those difficult situations in order to validate and verify the models, the behavior of the whole system. So in our case, 51 supports vector databases and plugins to search for images, but there's no support for multiple dataset, no point clouds data. So what Edward did is to design an approach to search across those modalities and dataset, and it's suitable for petabytes of data. So here is a little video where we can search through dataset that we have. So as you kind of seen about Alexandria and auto notation, but here you can pass in a URL, an image, a file, or a path. You can choose if your query is going to be images, point clouds, or text. So this is why it's multimodal. And here we're going to search through images. So we're going to search the text, a busy city center with pedestrian and buses, and we're going to ask to see the images related to that. And so this is now what embedding models do seem to see as a busy city center with pedestrian and buses. Now, what's quite cool is that you can do the same search now, but in point clouds. So you can start inputting the same thing, search across as many logs as you want, but this time you say, I want to have point clouds as output. You can input text or another point cloud or another image. This embedding space is multimodal, which means that it's going to work across any of those modalities. It's common space for the language, the images, and the point clouds. And now you're going to see point cloud representations. These have been colored as well so that they make the visualization a bit more comfortable. But there are colored point clouds about what you'd see, what you'd expect. So this is quite an awesome tool that Edward's made. Now, another thing that we can do is based on the similarities and also the auto-labeling that we have presented before, we can now search and annotate within datasets. So the good thing is that instead of labeling everything and searching for the labels, we use the embeddings to search faster the right images and then annotate them. So here you could, I don't know if the video was too fast or not, but basically was about searching speed limit signs within images. And then now another one that's, I'm guessing, the icing on the cake, the cherry on top, is now you can search spatially white vehicles within a log, and it's going to search them in the 3D space. And so as soon as you're going to see, we're going to swap to the LiDAR frame where all the images have been sort of isolated. The white vehicles, you have 3 of them, and you can even go further because embedding space are quite flexible. If you specify the model of a car, for example, white Lexus, you will be able to see it. So it is quite handy. Now, another thing that's quite important is that augmenting images. So something that we can't stress enough, right, is that collecting, filtering, and all that is not always enough to capture the whole data distribution. For example, there's only fog, right, usually early in the morning, but sometimes you might not be able to capture it all day, every day, because your capture vehicles are somewhere here and the fog is 50 miles away. So it's going to be a hassle to get there in time, and sometimes it's not possible. And sometimes long tail effects and rare events need to be addressed. Here in the UK, it doesn't snow that much. So how do we observe for the one day in the year, the snow, and avoid the models to go all wrong, whether it's vision models or reinforcement models, everything? We need to simulate this. And so here, this is a work called Sensor Expansion made by both Chem and Benjamin. And this here, we need to augment the data. So what they've made is a pipeline, that takes this original image that you see on the top left, and you can augment it with things like night, rain, snow. You can also in-paint details and ask for more things to be added to the model. So it's quite interesting. One thing that we are also working on right now is temporal consistency, to be able to generate video that are temporally consistent. And we want to ensure, one thing that is very key when it comes to autonomy, is to ensure that the semantic and stylistic consistencies are there and kept. That we want to make sure, for example, if we go back to that this car is still of the same color, but we can change the environment around it, the effect of light, etc., etc. This tool is available on Google Cloud Marketplace. So if you're interested, type GCP sensor expansion and it'll show up. And if you want to use the tool or anything, they'll be more than happy to provide guidance if you had a question, but there's quite a lot of explanation already. Now, finally, I guess to show that I'm not a crook, or at least not too much, is model training and validation. So here we design a little package to train models for any task, model, data, and machine. It's been designed as based on PyTorch and PyTorch Lightning, if you guys are familiar with it. And we're basically forcing anyone that develop machine learning models to be rational, to make reproducible code and exportable code. Because if your model is great but can't run in the car, is of little use. It's a nice curiosity, but it's not useful. You useful for the rest of the company. And some things that we do is automated hyperparameter search distribution to compute clusters on Kubernetes within the cloud and all this. So it's quite nice. It's quite tight. So here I'm going to show you a little result about this whole journey and how we got there. And to show the little point I'm making is that data is far superior than a model. So the model I'm going to show now, this is faster RCN, a model from 2015. It is a toy model. I will make a disclaimer. This is not the model that is deployed in the vehicle, but this is what I'm allowed to show today. So we're going to stay with that. We use the taxonomy of 80 driving related classes. And just to show, this video is on the test partition. So this model has never seen any image that was geolocated 100 meters closer than any frame that you see here. So to make sort of truly sort of test time data, like real life condition and not just overfitting on a set. So if you just allow me, I'm going to switch to a little better video because Google tend to be a bit aggressive when computing, well, when encoding those things into their own YouTube. So here you can see, basically, you see all the things, the tire, the street lights, the windows that you have on the cars, the license plates, all the cars. There is no post-processing being applied. This is the raw output from the faster RCNN. And basically, this is a faster RCNN trained on 1 million nicely curated image from a bit less than 100 hours of driving, of data collection. And so you can see nicely detecting all those lines as they come closer. You can see the signs on the sign, quite a high precision and very good recall as well. So we're very happy with this. If we go to like, I don't know, I'm guessing some quite crowded scene. There's no temporal tracking. Once again, each frame has been seen independently. There's nothing whatsoever. And things tend to be quite detected. We're looking at drivers, passengers inside to see intent, if there were any. Sometimes we can get away messages like these. So yeah, that's about this. I can let the video play for a while, or we can come back to that later. Depends if you're interested or not. I guess I'll come back to it maybe. But yeah, the conclusion is that, well, today I hope I have presented in an intelligible way some explainable and scalable automated workflow that goes from data collection to in-vehicle deployment. We have presented something that's very cool as a search engine for anomaly detection and validation and verification. We have a whole bunch of pipelines and data augmentation tool to generate out of distribution data that you could not capture. And that enables us to build robust families of model. Now, in the future, our team is working nowadays on general geometric 3D scene understanding and controllable 4D scene generation and augmentation. So now we are taking it one step further and basically building on this current pipeline and just adding more things to the sauce. Okay, so I think, yeah, I've reached the end of my presentation.